welcome to Mavinhub YouTube channel. In this video, I'll be talking about the 2021 NECO Physics Practical instruction. I'm going to talk about some of the things you should be expecting in the 2020 NECO Physics Practical, and I will also perform a simulation of what you should be expecting in the exam. So this video will not just talk about what you should be expecting in terms of the apparatus, but this video will show you how to carry out the experiment. But this time around, we will use our virtual environment to simulate the experiment. We'll be able to get results, we'll be able to plot graph, and we'll be able to change various parameters. So let's get into it. So the first thing you need to understand is you are going to be presented with a list of apparatus, and for the first question, here are the apparatus you should be expecting. You'll be given a retort stand, a split cork, a spiral spring, a mass hanger whose weight is 50 grams. You'll be given 4 masses, like slotted masses. You'll be given a stopwatch, and you'll be given a meter rule. Okay, so in this experiment, what you expect to do is this. You expect to hang a spiral spring on a retort stand, then suspend a hanger, and then have some weight on the hanger. Then you'll be asked to oscillate the spring and take some measurements. I'm going to show you our simulated environment that gives a similar result as this. So let's take a look at the simulated environment. So this is Mavinhub Physics Lab, and I'm going to walk you through the experiment that you'll be expecting in NECO 2021, NECO Practical, Physics NECO Practical 2021. Okay, let's take a look at it. So this experiment that you'll be expecting, that's question number 1, is known as oscillating loaded spring. Based on the apparatus that NECO has stated, the experiment is known as oscillating loaded spring. And the main goal of the experiment is to determine the stiffness of an oscillating loaded spring. So let's take a look at the diagram. The diagram is as follows. The diagram consists of a retort stand. You'll be given a retort stand, you'll be given a split cork. So this is how a split cork looks like. This is the spring. This is the slotted mass, and slotted mass is together with the mass hanger. The mass hanger is connected to the spring, and the mass is placed inside the mass hanger. It's just like a tool for suspending the mass and for connecting it to the spring. Okay, so these are the apparatus, very similar to what you'll be expecting. Okay, let's take a look at the procedure. There are 8 procedures that you need to take a look at, because the apparatus given to you will require you to do the following. Number 1, you'll be asked to suspend the spiral spring vertically from the split cork. The second step is you'll be asked to suspend a mass of M on the free end of the spiral spring. In the case of NECO, there will be a mass hanger on which the mass will be placed on. From the apparatus given, the mass of the mass hanger is 50 grams, and you've got 4 sets of masses. The third step is you'll be asked to pull the mass gently downwards, and you'll be asked to release it and to set it into oscillation. Then you'll be asked to determine the time to complete complete oscillation. What this means is you'll be asked to record the time it will take for these masses to complete complete oscillation. This value of n is unknown at the moment. You will get to know that during the experiment on the day of your exam. So this n could be 10. In other words, you could be asked to record the time it would take for 10 oscillation. The n could also be 20. You could be asked to record the time it takes to go through 20 oscillations. The interesting thing here is on Mavinhub Physics Lab, you can set the value of n the way you want and see the result under different values of n. So this will help you get acquainted with different settings and even give you result that may be very, very close to what you get at the end of the experiment in your laboratory. Okay, the fifth step is to evaluate the period t. Period is the time taken for n oscillation divided by n. In other words, you divide the time taken for, let's say n is 10, the time taken for 10 oscillation, then you divide that by 10. Then after computing the period, you look for the square of the period. Okay, you repeat the above procedures. In other words, you repeat procedure 2 to 5 for different values of n. That is, you will change or increase the mass and measure the time taken for n oscillation, then compute the period and the period square. Then you tabulate all your readings. The next phase is to plot the square of the period on the vertical axis, in other words, on the y-axis, and you plot m on the horizontal axis. Then you determine the slope of the graph and the intercept I on the vertical axis. Okay, what are the precautions to be taken in this experiment? You need to ensure that the load is gently pulled downwards by a small displacement. But you need to understand how to express this in your when asked in the exam. You should state it like this. You should say something like, I ensure the load is gently pulled down by a small displacement. I ensured zero error of stopwatch was noted and taken into account. I ensured that error due to parallax was avoided when taking reading from stopwatch. I ensured drought was avoided. So this is how you will state it when asked to list some of the precautions taken in this experiment. So the next part is the principle. So what is the principle behind this? What's the governing equation behind this experiment? Okay, let's take a look at all the notations here. There is a relationship between the period, that is the number of the time it takes for one oscillation. There's a relationship between the period and the mass and also the force constant of the spring. The force constant of a spring is a measure of how stiff a particular spring is. So if the force constant is very high, it indicates that that spring is really stiff, such that a very large amount of force will be required to compress or stretch it. So a spring with low force constant means it can be easily stretched by a very small amount of force. So it means there's a direct relationship between T and the square root of m, and there's an inverse relation between T and the square root of k. So this means that if we have a higher mass, if we increase the mass, we expect the period to increase. But in the case of K, if we have a spring that is less stiff, it means the period goes up. That is, the smaller the stiffness of the spring, the higher the period. Then the stiffer the spring, then the higher the stiffness of the spring, the lower the period. So let's try to square both sides. If you square both sides, you're going to get t squared equals 4 pi squared times m over k. So you will get this if you square both sides. Then let's try to represent 4 pi squared over k with s. Let's use s to represent this. If s represents 4 pi squared over k, you will realize that the equation will become something like t squared equals s times m. So the s in this case represents the slope. So basically, the principle behind this equation is such that the square of the period is directly proportional to the mass. Then the S is the slope of the graph that we are going to compute eventually. So which means if we want to compute the value of K, which is the first constant, we'll simply take 4 pi squared over S. We'll just make K the subject of the formula now as this. So which means at the end of this experiment, you may be asked to compute 4 pi raised to power 2 divided by S. You may be asked to multiply that constant too, but this is you should be expecting to see something like this in your experiment, at least in the actual physics experiment, because the objective of this experiment is to determine the force constant, and you can determine the force constant from the slope using this formula. Okay, so we are under the settings. So under the settings, you'll be expected to change the reading range. So this determines the readings that you will take. Then this section determines the constant. So constant like what should be the stiffness of the spring, what acceleration to gravity should we use. So in this case, we are using the Earth's acceleration to gravity. In this case, we're going to use a stiffness of 10, and the displacement of the spring will be 10 before letting it to oscillate. The number of oscillation, which is n, we are going to use 10 for number of oscillation before taking reading. Now for this section is determined by the information provided by NECO. So let's take a look at the information provided by NECO. Here we've got the information provided by NECO. We were told that the weight of the mass hanger is 50 grams, and we've got four masses. You understand? So four masses altogether making 80. So which means the minimum weight we should have is 50, and the maximum weight is 50 plus 80, which is 130. So let's go to the simulated environment. So here we are going to set the minimum to be 50 and the maximum to be 130. And we are going to set the step to be 20, since we'll be adding 20 grams for each step. So now that we've got our settings, then we are using time of the time we're going to spend there with that we'll be allowed to spend is 30 minutes. Let's start the simulation. So here's the simulation environment. So here we've got our weight hanger, which is 50, and we've got our spring and the cork and the retort stand and our stopwatch. Okay, here you've got the masses. So we're going to start with just oscillating the weight hanger, which is 50, then we'll add 20 gram, 20 gram, then altogether it's we've got 130. We're going to record the time it takes to complete one oscillation, the time it takes to complete 10 oscillations, and we'll compute the period, which is the time divided by 10. Then we'll compute the t squared. Okay, let's commence the experiment. So to start the experiment, you click on this in our simulated environment. To start the experiment, you click on the start. Or in the real experiment, to commence the experiment, you will stretch this mass downward and allow it to oscillate. At the point of oscillation, you need to count the number of times it oscillates. So let's take a look at this. So I'm going to click on start. Then there will be a countdown. Then let's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for 10 oscillation, we've got, let's take a look at what we've got. So you can use your magnifier to see what the value is. So what I'm going to do here is I'm going to start all over again because I think I was not so fast enough. So let's start again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 10 oscillations. So let's check what the value is. So very similar to what we got earlier. So let's take this to be, this is 1 second, 2, 3, 4. This is almost 5. That's 4. Let's take 4.8 seconds. 4.8 seconds. Note that the result you get is a function of the spring constant. So if you have if you increase the stiff constant, the time it will take will be smaller for 10 oscillation. And if you reduce the spring constant, it will take a longer time to complete an oscillation. So just note that the results we are getting here is strictly based on the settings of our spring constant. But if you set your spring constant to be exactly what you have in real world, you will get the same answer as that of a real experiment. Okay, let's record what we have. So the time is 4.8 seconds. So what is the period? The period is 4.8 divided by 10, which is n. So you can take a look at the procedure. The period is t divided by n. And what is n? N is number of oscillation. So n is 10, number of oscillation. So you divide this by 10. So that is 0.48. In some cases, you may be asked to take two readings. So there could be a T1 and a T2. So the T1 could be the first reading for this same setup. Then the T2 is like a repetition of this experiment. Then you'll be asked to take the average. It's a common practice in physics to take two readings, then you take an average so that the average might correct any error that you've got in one of the readings. You understand? So, but in this simulated environment, you are just expected to take one reading and proceed. Okay, the next thing is to get the square of the period. So what's the square of the period? So let's launch the calculator on this system. So that's 0.48 raised to the power of 2, and that's 0.2304. So 0.2304. So that's the first, that's for the first reading. So let's adjust the weight, the mass rather. So let's increase the mass. Let's add 20 to 50. So that's 70 altogether. So now we've got a bigger mass. And now let's run the simulation again for 10 oscillation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so let's take our reading. So this is about 5.5 seconds. So 5.5 seconds when the total mass is 70. So if you divide that by 10, that will give you 0.55, and the square of that will give you 0.55 raised to the power of 2, and that's 3025. So the next is when the mass is 90. So let's add 20 to it. So that gives us 90. So let's run the simulation for when the mass is 90. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's take our measurements. So on the stopwatch, we got let's say roughly 6.2. So roughly 6.2. Then the period is 0.62. That's the t divided by 10. Then when you square that, we're going to get 0.62 squared. So that's 0.3844. 0.3844. So let's increase the mass by 20. So that's 110. Okay, so let's run the experiment and count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 6.2 Let's say 6.8, because after you have a 5, then that's 6, then it's almost 7. 6.8. That's 6.8. Then that's 0.68. Then when you square 0.68, that will give 0.68 squared, and that will give you 0.4624. 0.4624. Okay, so let's run the experiment for when the experiment is 130. When mass is 130. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is 7.2. So that's 7.2. So let's say 0. So that's 0.72. Yeah, and this is the square of 0.72 is 0.5184. 0.5184. Okay, so we've got our readings. We've completed our reading. So let's take a look at the instruction. The instruction states that we should plot a graph of t squared on the vertical axis and m on the horizontal axis. So t squared will be on the y-axis and m will be on the x-axis. Now let's go to the graph section. Under the graph section, you'll be expected to specify the title, the x label, the y label, and the range. So let's take a look at the title. So what should be the title of our graph? The title should be period square versus mass. So let's set the x label. The x label, we have our mass on the x label. So we can say m, and we state the units, which is in gram. Then on the y axis, we've got our period square. So we can say t square, and the unit is in seconds. That's period. This is seconds. Okay, so what about the minimum value of our graph? So what should we set as the minimum value and what should we set as the maximum value? That's a skill set that that we are going to explain in a separate video. So the video will be dedicated to how to determine the right scale for your graph. So just check our YouTube channel for details on that. But a quick way to get your scale right is to look at the maximum value and the minimum value of your x-axis and y-axis. So on the x-axis and y-axis, I have 130 and 50. So just take the difference. The difference is 80. Then just divide the 80 by 8. So that gives you 10. So this is a rough estimate of how you can get the right scale. So 10 means your step should be 10 and your minimum can be minus 10 in this case. So let's quickly do that. But there are special cases where you have to take care of rounding off and all of that. We'll explain that in a separate video. So this is minus 10 and um, this is the minimum is minus 10, maximum is 140, and we have a step of 10. Then let's take a look at the y-axis, this the scale for the y-axis. So we know the minimum, the maximum to be 0.5184, then divided by the number of lines, the number of major lines that you want to have. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So then the number of major lines minus 2. So that's divided by 8. And that will give you this. So the issue here is we can't use this as our step, right? So we have to round it up or down, but I will go into detail in the video on how to get the right scale. So I'm going to round it down to 0.05. That is the most appropriate in this case, 0.05. So I'm going to round down 0.05. Then okay, let's take a look. So this is 0. I'm going to use 0.05. Then the minimum is, let's start with 0. Then let's make the maximum to be the maximum value here plus 0.05. So that's 0.55. So that's 0.55. Yes. Then we can start from we can't start from 0 because our graph will be sort of tiny. So let's start from the minimum minus 0.05. So let's say roughly 0.15. Okay, so is this is just a process that I need that you have to go through to choose the right scale. But stay tuned for details in our upcoming videos. Okay, now we've gotten our scale and we've labeled our axis. The next thing is to locate the point on the graph. In other words, um, we need to locate each of these points on the graph. So when m is 50, we need to locate 0.2304. So when m is 50 and m is 50, the t squared is 0.2305. So where is 2305? So 50, 2305. So here we have 2, 3, 2 threes here. Then this is roughly where we should go. Okay, so before you click, you have to highlight this pencil to indicate that you want to locate the point. So now that we've highlighted it, so this is 0.2304, roughly 2304. So when m is 70, this is m 70. What is the value of t squared? That's 0.3025. 0.3, this is 0.3. Then this is 0.31. So we are not going to get 0.31, so it's somewhere here. 0.25, so 3025, which is somewhere here. So now we've gotten the second point done. Then the next is to determine the next point, which is 90. When m is 90, then we have 0.3844, 0.3844. So this 3 8, these 3 8s, then we have 4 4. So this is somewhere here. Okay, so the next is when m is 110, that's this. Then we have t squared to be 0.464624, 4624, which is somewhere here. Okay, so the next is 130. When m is 130, then we have 0.518, 0.51851. 8, which is somewhere here, 5184. Okay, so now the we've got our lines, our points located. Okay, so I'm going to increase the y-axis to 0. So let's start from somewhere like 0.0 minus 0.05. And I'm doing this because I would like us to uh, cross the intercept, the y-intercept. It's part of the question. So if you're asked to get the y-intercept, the zero, uh, the zero origin has to be visible. So that's the reason why I'm going to start from a negative value for the y-axis. Okay, so now let's talk about the graph slope. So how do you get the graph slope? You need to get the graph line. So once you've located the point on the graph, the next phase is to draw the line. So to draw the line, all you need to do is since we wanted to cross this point, so what we need to do is to start somewhere and just click any point on this graph. Then just move the cursor. You don't need to drag, just move the cursor, then it will tell you whether you are getting it right or not. So we have this. So I'm going to delete this because it appears that um, it's the line is not going through. So let's pick the pencil again and draw it again. You keep doing this until you believe you've got a good line of best fit. Okay, so let me stick with this. So the next phase is we've got our line of best fit. The next phase is to get the graph slope. So the graph slope, you just pick any 2 points on your line of best fit. So I'm going to pick this point and this point. Okay, so the next is to determine the x1 and y1 from this first point, and to determine the x2 and y2. So what's the y1? The y1 is the line, if you extend this to this point, so which is roughly 0.23. So 0.23, then y2 is roughly this 0.45. Then the difference is 0.22. So now we move on to x. So x1 is 50 and x2 is 110. So the difference is 60. So what is slope? Slope is change in y divided by change in the x. So which is 0.22 divided by 60. So that will give us 0.0037. So 0.0037. Okay, that's the slope. So we've got our slope and we've completed the graph. So this software guides you on how to draw a proper graph, from setting your title to setting your labels to defining the scale on the x-axis to defining the y label, the scale on the y-axis, to identifying the point on the graph, to drawing the line of best fit, and to getting the slope. So it walks you through the whole process. You get to do it by yourself and you get to make mistakes, get yourself corrected, and so on. Now let's move on to the question section. You'll be asked some questions, a kind of follow-up question based on your graph. So let's take a look at the question. So the question states that we should evaluate k equals 0.001 times 4 pi squared divided by s. So we know our S, which is the slope. Our S is the slope, right? So we know that the slope is 0.0037. 0.0037. So what is the value of K? So all we need to do is to say 0.001 times 4, then times pi, then times pi, then divided by 0.0037. So that will give us 10.67. So we got 10.67. So that's the value of the K we've calculated. Okay, so what about this other question? A force of magnitude 500 Newton is applied to the free end of a spiral. This is a question, an extra question based on the topic of this experiment. So you have a force of 500 Newton and is applied to the free end of a spiral spring whose force constant is 10,000. Calculate the energy stored in the stretch spring, and your answer should be in joule. Okay, so let's solve this question. So I'm going to walk you through the solution to this question. So let's take a look at the question, the solution to the question. We know that the force is 500 Newton. Then we know that the force constant is 10,000 Newton per meter. So the question says that we should calculate the energy stored. The energy stored is the question. This energy stored in the spring when being stretched by this force, and it has a force constant of this. We know that energy stored in a spring is Fe divided by 2. The work done to store such energy is Fe divided by 2. And since based on Hooke's law, F is equal to Ke, where E is the extension as a result of the force being applied. So we can say that since we know the K, we know the K value, but we don't know the E, we can represent the E in terms of F and K. So we can say E equals F divided by K, right? So we can substitute this E here to get F squared over K, then divided by 2. So this is another way you can represent the energy, the square of the force divided by 2 times the force constant. So now let's substitute. So F equals 500 squared divided by 2 times 10,000, and that will give you 500 times 500 divided by 2 times 10,000, and that will give you this. So at the end of the day, you have 25 over 2, and that will give you 12.5 joule. So the answer to that question is 12. So let's type the answer. So the answer to this question is 12.5. So now we've answered the questions, we've done the plotting, we've taken our reading, we've got the lab session done. So the next phase is to submit. This software has the ability to analyze your work, grade your work, and give you detailed feedback on how you perform. So let's submit. Okay, so after submitting, here is our performance. Okay, so the first thing is my reading. My reading performance is 60%, and my graph axis is 31.2%. My graph point is almost perfect. My graph line is almost perfect. My graph slope is very good. But the question, so let's take a look at what happened. So in the graph, in my reading, I made some mistakes with some parts of my reading. So now this software has a way to grade you in such a way that you may not be perfect, but you need to be about 95% close to the actual answer. So since um, my answers are a bit close, but because I wasn't meticulous enough, it was able to dictate those errors. So this means you have to be very careful when taking your reading. If you don't take the reading on time, if you don't stop the stopwatch on time, you are going to get readings that are not going to be close to the actual reading. So this is just a demonstration of some of the issues that you may encounter, and that's the whole essence of practicing. So if I were you, I would go ahead and practice again until I perfect my act of stopping the timer at the right time and all of that. So that's the whole essence of this section. Is just make you understand that you need to be very meticulous and careful when taking readings, otherwise to affect a lot every aspect of your results. Okay, so um, this section is the reason why I didn't perform very well on the axis is because I extended the y-axis. I didn't get my scale right. So let's take a look at the results. So the result here is a bit different from the actual result. The actual result is meant to be 10 because that's the first constant of the spring we used. So I got it wrong because I'm not 95% close to the answer. If I happen to be about 95% close, then I'm going to get it right. And the reason why I got this slightly different result is because my readings here affected it. Once your reading is faulty, it's going to have a ripple effect on your slope. So ensure that your reading is very good so that it doesn't affect your slope. Okay, so the one I got this correctly because that's the actual answer, 12.5. So this is just a simulation of NECO Physics Practical 2021, and what you should be expecting in the exam will be very similar to this. You'll be asked to take the following measurements, you'll be asked to plot graph, you'll be asked to find the slope, and you will also be asked to answer some questions based on your slope. So another one important thing you need to take note is getting your scale right is very important, and also getting your readings right is very important. So uh, what I would expect you to do is to get the Mavinhub Physics Lab, download it, and just keep practicing until you can get at least 90% score so that you'll be confident enough to get it right in the actual exam. And also note that this software produces very similar results to what you will obtain in the physical lab. So that's one of the things you have to understand. So thanks for your attention, and thanks for listening. All the best in your exam.
To simulate physics experiments virtually, visit our website at www.mavinhub.com to download Mavinhub Physics Lab. Link in the description below. Don't miss a video. Click the subscribe button and the notification bell to get notified when we drop a new video.